Okay. Oops. All right. So this is the molecule that you're talking about, right? So the skeleton structure just tells you which atoms are connected to which atoms. But I don't expect you to know that that's the skeleton just by looking at that. Eventually, if you're going on to organic chemistry, you'll do enough of these that you'll realize that there are only certain ways that you can connect these. But when you go on to organic, you end up having so few atoms with so many different permutations that having skeletons is almost necessary all the time. Does that make sense?
Yeah. Wait, so is that the skeleton structure?
That's the skeleton structure. It's not the Lewis structure, right? But this is what I would give you in order to get you started with a problem like this. Does that make sense?
Wait, so this is like the skeleton structure for... So basically this is like the general structure of...
This is how the atoms are attached to each other. This is how the atoms are attached to each other.
Okay.
Right? So this isn't the Lewis structure, right? But this is the...
You have to draw on the electrons and all that. Okay.
Right? So this is not uncommon in terms of questions that I'll ask you, where I'll give you some kind of skeleton structure and ask you to complete the Lewis structure.
Mm-hmm.
Whoops. So the way that you would complete a Lewis structure from a skeleton is exactly the same way that you would from the chemical formula, right?
Right.
So for this one, we would just start by finding our total valence electrons.
I think it's 20.
So we have hydrogen has 1 electron, carbon has 4 electrons, and there's 2 of them. Nitrogen has 5 electrons, and oxygen has 6 electrons. So we got 8 plus 12. Is that 20? Yeah, did I do that right?
Cool. Yeah.
All right, so we have 20 total valence electrons, and we have 2, 4, 6, 8 electrons used in bonding. So we have 12 electrons left over, right? Am I going to put any lone pairs on hydrogen?
No.
Why not?
Because it can only carry 1 electron.
It can only have 2 electrons around it, exactly.
Oh, yeah. Definitely sharing it.
Yep, so I'm going to start putting them around oxygen. So I've got 6, 7, 8, 9, 10, 11, 12. Okay. Now, where I chose to put them is pretty arbitrary, right? I could have put them on carbon too, but it doesn't matter. Does that make sense?
Oh, it doesn't?
Not at this point, because what my next move is going to be is to evaluate the structure, right?
Okay, I thought you meant... Okay.
So whether or not I put 3 lone pairs here or 2 lone pairs here and 1 lone pair here, the outcome is going to be the same because I have to satisfy the octet for everybody. So I know, just looking at this, octet is not satisfied for several of them, which means I'm going to have to share some electrons. Does that make sense?
Yep.
Cool. So, first guy, hydrogen can, hydrogen can only have 2 electrons. It has 2 here. It's satisfied. Carbon has 2, 4, 6, so it's not satisfied. Carbon here has 2, 4, so it's not satisfied. Oxygen has 2, 4, 6, 8, and nitrogen has 2, 4, 6, 8, right? So here we have the 2 carbons are lacking an octet, right? So what should we do to try and satisfy those octets?
I did a double bond between hydrogen and carbon.
So moving a lone pair in here, right? What about the other carbon?
I don't know. I don't know if you want to do like lone pairs or a double bond. Yeah.
Let's just double bond because we know that nitrogen has a satisfied octet, right? So what we're trying to do is share electrons. When you see that you have a satisfied octet next to an unsatisfied octet, that should be an indication that you want to start sharing electrons. Does that make sense?
Mm-hmm.
So
You can add another bonding pair to the carbon.
Like I just did here?
Oh, yeah.
Mm-hmm.
Oh, I think you're going to do a triple bond. Wait.
I think you're right. But let's evaluate just like this so we can see what the structure looks like and go from there. Okay, so after I do this, I'm going to rewrite my structure.
Yeah, that way you satisfy the formal charging